In this module, what we are going to do is we are going to apply the renewal reward process that has already been introduced in an earlier module. We are going to carry on with applications of this, and in this module we are going to focus on one particular application, which is a queuing application where there is a single server. So the model would be like this: customers arrive, there is an arrival process, arrival sequence, and then if a customer finds the server free, then service starts immediately. That's when a cycle starts, and then this uninterrupted busy period continues, and then maybe the uninterrupted busy period ends at some point of time, and then when the next uninterrupted busy period starts, that's when a new cycle starts and the old cycle ends. So here are two distributions that are important. One is the inter-arrival distribution of the customers, and the other is this IID service times of the different customers. So one is called X, the other is called Y, and we assume that E of Y is less than or equal to E of strictly less than E of X. That is, the expected service time of a customer is less than the expected inter-arrival time between successive customers. So anyway, under these assumptions, we basically study two things and prove a very, very widely used result in queuing theory. One is what is called a time average of the customer density, and the second is the average waiting time per customer, and we look at the limits of these two things. We show that with probability 1 they converge to two different constants, and then we prove a relationship between these two limits, which is a very widely used result in queuing theory. So we look into a queuing application with a single server. So arrival is assumed to be renewal process with inter-arrival times x1, x2, x2, etc., etc. And the successive service times are y1, y2, etc., again assumed IID. And we make one more assumption, namely EY is less than EX and EX is finite. And the standard thing, namely that when a customer on arrival finds the server free, there is only one server, a customer on arrival finds the server free, the customer immediately starts receiving service, otherwise the customer has to wait in a queue. Okay, so let Ns be the number of customers in the system at time S. So what we want to know is, or show, integrate Ns from 0 to t with respect to ds, divide by t. So this is sort of number of customers in the system averaged over time average of the number of customers at various points of time. So that's what it is. What we're going to show is, as t goes to infinity, this average, time average of the number of customers, converges with probability 1 to a constant L. So even though that average, time average of number of customers is random, but it converges with probability 1 to a constant L. So as we said, 1 over t 0 to t ns ds represents the average number of customers present in the system during the time 0 to t. So this is a time average. We get the above result by application of the reward process, renewal reward process, which has been stated earlier. First of all, let's describe the renewal process that we are going to consider. The renewal process that we consider here is one where, first of all, a new cycle starts every time a new arrival finds server free, okay, which means that a cycle is really a busy period. Note that when a new cycle starts, the newly arrived customer immediately starts getting service, as we said earlier, and the cycle continues until after completion of an uninterrupted busy period initiated by the first customer. The next customer arrives to find the server free again. So that's how it continues. Okay, so is that should be clear. We have seen this before also in the context of Poisson process. So in other words, a cycle starts with the start of an uninterrupted busy period and continues until the start of the next uninterrupted busy period. So the cycle includes and starts with the start of an uninterrupted busy period, and it does not end with the end of the uninterrupted busy period. That's important to remember. It ends only when the next uninterrupted busy period starts, which means the period from the end of a busy period till the time when the next uninterrupted busy period starts, this time is also included in the cycle. Since the system starts afresh every time a new uninterrupted busy period starts, this clearly gives a renewal process, because every time a busy period starts this way, a customer arrives and finds the server free, and therefore starts receiving service immediately. Next time when this same scenario happens, that is, after a busy period is over, there is a idle period when there are no customers, and then suddenly another new customer comes in and finds the server free. That's when the next cycle starts. So every time the cycle starts, the whole system starts afresh. So this is indeed a renewal process. Let capital T denote the typical time between starts of two consecutive uninterrupted busy periods. So T represents a typical length of a typical cycle, typical renewal cycle. So the lengths of the successive renewal intervals of our renewal process are IID with distribution T. Distribution has same distribution as T. One can show, which I am not going to do, that the assumption that EY is less than EX, which is finite, implies that expectation of T is finite. That is, expectation of the time between start of one uninterrupted busy period and the start of the next uninterrupted busy period, the expected time between these two has finite expectation. So this is something, it intuitively is clear, but we'll just accept this. So next we describe the reward scheme. Assume that reward is being earned at a rate ns at time s. Then RT, which is the total reward earned during the time 0 to t, would be simply 0 to t ns ds, because at time s you are earning the reward ns. So the integral of ns with respect to s from 0 to t would give you the total reward during 0 to t. Therefore, by the renewal reward process theorem, what we have is RT over t goes to E of r over E of t as t goes to infinity with probability 1, where r represents the total reward earned during a typical renewal interval. Reward earned during a typical cycle is of course r, which is 0 to capital T ns ds, because capital T is the length of a typical cycle. So during that period of time, the total reward earned would be integral 0 to capital T ns ds. So we conclude therefore that with probability 1 over t 0 to t ns ds converges to expected value of 0 to capital T ns ds divided by expectation of capital T, which is of course a constant as t goes to infinity. For the same queuing process, we now want to consider a different quantity and find its limit. Let Wi be the amount of time that the ith customer spends in the system. So what we proceed to show is this. Look at W1 plus etc. Wn divided by n. So what is W1 plus W2 plus Wn over n? It sort of represents the average time that a customer spends in the system, averaged over number of customers arriving. So we're going to show that this also converges to a constant W as n goes to infinity with probability 1. How do we do that? We do that again by using renewal reward process theorem. But we now use a different renewal process. The renewal process we use would be one where renewals take place only at positive integer time points. So let's see how that is done. So here's the renewal process. Recall the previous renewal process where renewals take place every time a new arrival finds the server free, or equivalently every time a new uninterrupted busy period starts. Let now capital N1, capital N2, etc. denote the number of customers served during each cycle of the above renewal process. So N1 is the number of customers, total number of customers served during the first uninterrupted busy period. N2 is the total number of customers served during the second uninterrupted busy period, and so on. One is absolutely clear that N1, N2, etc. are positive integer valued random variables, and that they would be IID, because successive uninterrupted busy periods are IID, and this N1, N2 are IID random variables. Each has distribution, let's say capital N, where N represents the number of customers served during a typical uninterrupted busy period. Now what we want to do is we want to consider a renewal process whose interarrival times are these N1, N2, etc., etc. Recall that each of these N1, N2, etc. have to take value at least 1, because an uninterrupted busy period starts with a new arrival finding the server free. So at least one customer is going to be served in any uninterrupted busy period. So N1, N2, etc. are not only IID, moreover they also take values greater than or equal to 1. Can show that the same assumption that we made before, EY is less than EX finite, implies that En is also finite. So earlier we showed that expected time between two successive uninterrupted busy periods, that has expectation finite as a consequence of EY being less than EX and finite. But we have now not only that, but we also have that the same hypothesis also gives that expected number of customers served during a typical uninterrupted busy period, that expectation is also finite. Now to apply reward renewal process theory, we introduce a reward scheme. So what's a reward scheme? The reward scheme is rewards are earned only at positive integer times, with reward at time I being Wi. And what is Wi? Wi was the amount of time that the ith customer spends in the system. So at time I, look at the ith customer, how much time that customer spends in the system. That is what would be the reward at time I. Then the total reward earned up to time n, which is Rn equal to W1 plus W2 etc. plus Wn. Now by the theorem on reward renewal processes, we have with probability 1, Rn over n, which is W1 etc. Wn over n, converges to E of R over E of n with probability 1 as n goes to infinity, where R denotes the reward earned during a typical renewal cycle, and of course n is the number of customers in a typical uninterrupted busy period. Now reward earned during a cycle in R is I equal to 1 to n Wi. Why? Because capital N denotes the number of customers served during a typical busy period. For each I, the reward amount is Wi. Reward is at the rate of Wi. So the total reward is summation Wi, I equal to 1 to capital N. So therefore we can conclude that with probability 1, W1 plus W2 plus Wn over n, as n goes to infinity, converges to expectation of, so we are now writing in place of E of R, we are writing expectation of summation I equal to 1 to capital N Wi divided by E of capital N, which let's call it W, which is a constant of course. We have just proved two interesting results for a single server queue by applying renewal reward process theory. What we have shown first was the average number of customers in the system, here I mean time average, which is given by 1 over t into 0 to t nsds, converges to a constant L with probability 1 as t goes to infinity. And then we have also shown average waiting time per customer, which is W1 plus etc. Wn over n, where Wi is the amount of time that the ith customer spends in the time. So this average W1 plus W2 etc. up to Wn divided by n gives you the average waiting time per customer. We have shown that with probability 1, that also goes to a constant W as n goes to infinity. It is clear that the average number of customers in the system per unit time, of course, and the average waiting time per customer should be related. Sort of intuitively, if the average number of customers in the system is large, that means that each customer would have to wait for a longer period, and that's exactly what I'm saying now. So larger customer density in the system, larger number of customers per unit time, so larger customer density in the system would surely result in longer waiting times for customers. That should be intuitively clear. Since L and W are the long run values of the customer density and waiting time per customer respectively, this relation should be captured in these two quantities. Now, indeed, as expected, there is a precise relationship between the constants L and W, which is quite an important result in queuing theory, especially for making managerial decisions, etc. This relationship is captured through an important parameter of the underlying queuing process called the arrival rate. So let me say what it is. So here is the widely used result in queuing theory. L happens to be lambda times W, where lambda is 1 over Ex, 1 over expected value of the typical renewal cycle. This is what is called the arrival rate. Of course, the proof of this result is not really an application of the reward renewal theory. It's actually a nice use of Ward's lemma. And here is a proof. This is very widely used in queuing theory. It's easy to see that the length t of a cycle beginning at the start of an uninterrupted busy period of the queuing process and ending at the start of the next uninterrupted busy period is related to the number of customers n served during a cycle through this relationship, that t equals summation I equal to 1 to capital Xi, where remember Xi denote the inter-arrival times between successive customers. Of course, recall exactly as I said, Xi's are the inter-arrival times between successive customers. Now to see this, note that if exactly n customers are served during such a cycle, then the next cycle starts when the n plus 1th customer arrives. To be more precise, if a cycle starts with the arrival of a new customer who finds the server free, ends up serving exactly n customers using including the initial customer, then the present cycle ends exactly after n more arrivals. Thus, t is a sum of a number capital N of IID random variables which are distributed as x. Now we want to apply Ward's lemma and find the expected value. So we check the conditions for Ward's lemma. We already know that E of x is finite, that's assumed. We have already noted before that E of n is finite. Finally, for any n greater than or equal to 1, the event capital N equal to n occurs if and only if x1 plus x2 etc. up to xk is less than y1 plus etc. plus yk for 1 less than k less than or equal to n, and if you look at x1 plus x2 plus etc. up to xn, then y1 that is greater than y1 plus y2 plus etc. up to yn. Thus, this shows that the event n equal to capital N equal to little n is naturally independent of xn plus 1, xn plus 2 and so on and so forth. So we can apply easily Ward's lemma to conclude that E of t is E of n into E of x, which is equal to E of n divided by lambda, and that gives that L is actually equal to W. Okay, so let me say that we have seen a large number of applications of the general theory of renewal process, alternate renewal process, reward renewal process, etc. There are still a large number of other applications in a variety of different contexts that we have not included here. But through the application that we have discussed, I think a special attempt was made to highlight the central ideas and definitions. As we said in the beginning, this entire module was focused on a queuing application, very important queuing application, which is very widely used with a single server. So the model was, there is an arrival process of customers determined by or prescribed by inter-arrival times x1, x2, etc., which are IID, and the other randomness comes from the IID service times y1, y2, etc. And as I said in the beginning, one fundamental assumption was that E of y is less than E of x. Under this assumption, first of all, we looked at two quantities of interest. One is, if we consider at time t or time s, ns to be the number of customers in the system at time s, we looked at the average of ns, time average of ns. What do you mean by that? Well, we look at 1 over t integral 0 to t ns ds. So we showed that the time average with probability 1 as t goes to infinity converges to a constant limit, we call it L. The other quantity that we looked at was the average waiting time per customer. So denoting Wi for as the waiting time of the average customer, of the ith customer, we look at the ratio 1 over n times W1 plus W2, etc., Wn. We showed that that also converges with probability 1 to a constant W, and both of these things were done by considering two different renewal processes and defining an appropriate kind of reward scheme and then appealing to the result of renewal reward process. So this is something that's worth looking into. And then by an application of Wald's lemma and another use, very nice use of renewal theory, we were able to actually show that there is a connection between these two constants, these two limits we call W and L. It turns out that W is related to L by means of what is called arrival rate, which is 1 over or reciprocal of the expected arrival time as expected. So anyway, so with this our module on renewal process also ends. We have tried to see throughout this, through these various modules on renewal processes, we have tried to first of build up the theory of renewal processes, stated some results without going into the detailed mathematical proofs, and then we focused mostly on how to apply this in various different kinds of contexts, which is what we did. There are many other applications which we didn't have a chance to explore here, but nevertheless, hopefully, the main ideas and the techniques, etc., have been introduced so that you get a picture of how important it's supposed to be.